how strongly finitary monads and varieties. Do you hear me? Good. So I'm very happy to be on this very nicely organized conference and grateful to this organization committee. I will talk about the joint work with Jirí and Dostal about how far can one generalize the classical bijection between finitary monads on the category of sets and finitary varieties of algebras, in particular to the categories important in computer science, where one does study enriched algebras like continuous algebras living in complete posets or quantitative algebras living in metric spaces. So let me first shortly recall the classical thing. So we have on the one hand side finitary varieties, and on the other side finitary monads. On the category of sets. And there is this bijection. When I say bijection, I really mean the serious thing, namely the category of all finitary monads and monad morphisms is duly equivalent to the category of varieties, where we work with finitary signatures, so index family of n-ary operation symbols, and a variety is of course a class of sigma algebras given by a bunch of equations. And what is an equation? It's just a pair of terms over some finite set of variables. Now, let me recall, finitary means preservation of filtered coordinates, or, if you want, you have the full subcategory of finite sets embedded into the category of sets, and to say that the set factor is finitary is equivalent to saying the factor is the left-hand extension of its restriction to finite sets. And one important property that follows from this is not equivalent but follows is that this factor preserves reflexive conqualizers. So, just to recall, a pair of morphisms is reflexive if it consists of split epimorphisms and has adjoint splitting, so represents a reflexive relation. Okay, so this classical thing has been generalized or extended by Kurz and Wellebill in 1916 to ordered algebras. So now we move from the universe of sets to the universe of posets, and recall that posets is a Cartesian closed category, so we can speak about enriched categories over posets, enriched functors over posets, which means locally monotone, and the result was completely analogous to the classical one if you move from finitary monads to strongly finitary monads. And this is a concept that in 1990s was introduced by Kelly and Leck in general CCC categories. So you have your Cartesian closed category. You have again a very analogous functor to what I mentioned before. Now it in general doesn't have to be an embedding. Namely, to every finite set you assign the finite copower of the identities of the terminal object. And what is a strongly finitary functor? It's one that satisfies this equation. So the one that's a left-hand extension of its restriction to finite sets. Now, for example, in the category of posets, it's clear what K does. It assigns to a very finite set a discrete poset. And on the side of varieties, there is no change except that you don't use only equations, you use in general inequations, which means an algebra satisfies this inequation if every interpretation of the variables where we are in leads to two elements in the algebra that are invariant. Okay, so this is the result. There is again a bijection between varieties and strongly finitary monads. Now, the paper had something like almost 40 pages, and you would have to extract it, extract the proof. In the last CD, I was referring about the joint work with already the same group, Dostal, where we presented a simple proof. And the essential idea, or a part of the essential idea is that we also characterize, so what are these strongly finitary things? The left-hand extension is an elegant but a bit abstract condition, and it turns out that to be strongly finitary is the same thing as to be finitary, preserved. Of course, now I already said, and I'll repeat it. Host is Cartesian closed, and when I say functor, I immediately mean enriched functor, so enriched, finitary, and preserves reflexive coincidence. So what is a reflexive coincidence? You have again a reflexive pair, and now either in POS or in whatever POS enriched category, it's a universal morphism with a property that CF1 is smaller than CF2. And using this characterization, we essentially proved the bijective correspondence much in the style of the classical result. Well, I would say it's pleasant that it's so close together, but not really surprising in the view of the fact that the category of posets is not only Cartesian closed, but also locally finitely presentable as a Cartesian closed category, so also the Cartesian closure is enriched. And then we started to think about these categories, as I mentioned, used in computer science. For example, the category of CPOs. So I will distinguish between CPO and DCPO here. So CPO is a poset with countable, joins of omega chains. So these are the objects. The morphisms are continuous functions, that is, functions that are both monotone and preserving these omega chains. And on the side of varieties, so I'm still the same thing, the finitary signature and finite sets of terms, but now I have to work with extended terms. So what is a term non-extended? A term is recursively defined either as a variable, or you take an n-ary operation and terms and form a term of this form, and by extended I mean take whatever sequence of terms and write a new term as a formal join, and so now you are allowed to make inequalities between extended terms. So that's on the side of varieties. How about monads? So our result is that varieties again correspond bijectively to strongly finitary monads. Defined again as the left extensions, and the characterization is the same. These are precisely the factors, the monads enriched over CPO. So this time the functor has to be locally continuous, and they preserve filtered colimits and reflexive coincidence. And the gist why it works is if you start with proposition which makes it tick between strong infinitarity and this preservation is that the category of CPOs, exactly like the category of offsets, is a free completion of finite sets, now considered as CPOs, under filtered colimits and reflexive coincidence. How does this work? Well, you start with finite discrete posets. Now you make reflexive coinserters and get all finite posets. How? Well, if you give me an arbitrary finite poset, I will take as y its underlying set, as x the order as a set. Here you have the two projections, and their coinserter is P. Now, using finite posets, you will get, by filtered colimits, the following CPO. Natural numbers, it's not a CPO, but natural numbers with a top element is a CPO, because, so I'm writing a bit bigger. Here is a CPO, and now take the following omega chain of finite chains, and the colimit in the category of CPO is this poset. And if you take finite copowers, it's the same thing, right? Then you take the finitely many powers of this and this. So by using filtered colimits, you get all these CPOs. Sorry, by using, yes, filtered colimits, you get all these CPOs. And now the fact is that you get all the category of CPOs by the fact that every CPO is actually a filtered colimit of the comma category from these objects. And then one uses the theory of three conditions by Kelly and Schmidt, and gets the result that the CPO is this preconditional. And so with this characterization of strong finitary monads, we were able to prove again this bijection. The next one would be the category of DCPOs. It's a very similar story. A DCPO is a pole set with direct joints. And if one says now, morphism is a continuous function, then continuous now means preserving direct joints. And so on the side of varieties, you need extended terms which go a bit further than before. So you need formal joints of directed pole sets that are not too large, so the cardinality is at most 2 to the cardinality of the signature plus -0. And so this is an extended term. You have your varieties given by inequalities. By the way, varieties of continuous algebras were in the 1970s hot topic in theoretical computer science. For example, the Birkhoff variety theorem was proved by Evelyn Nelson, Jan Reiterman, and myself. So, okay, so these are situations in which, again, strongly finitary monads bijectively correspond to varieties of algebras. And now I come to a moment where I have to apologize to all of you, because in my abstract I was claiming more than I can prove. Was not intentional. So what I'm now coming to are quantitative algebras. This is a hot topic of these days. So Adámek, Plotkin, and other co-authors published in the last 5 years a series of papers about algebras where the base category is now extended metric spaces, so metric spaces with infinity allowed as distance, and non-expanding matrices as morphisms. And so on the side of the sigma algebras, I again use the same thing that I use all the time. So signature in the classical sense, term in the classical sense, but now instead of equations they use quantitative equations. Here this epsilon is a non-negative real number, and to satisfy such an equation means you have your algebra enriched by metric spaces, and whenever you interpret the variables you get 2 elements of distance at most epsilon. Now, we have, of course, a very canonical embedding into this category. Every finite set is a discrete metric space. All distances are infinity. And therefore, we again have the concept of a strongly finitary monad. Well, what we don't have is Cartesian closedness. And that's the mistake that the three authors did, namely, in a very interesting paper by Kelly and Leck, did I mention already that they introduced strongly finitary monads? They also prove that a composite of strongly finitary functors is strongly finitary, and that's what we used at one stage in our rather long proof, until somebody told us, moment, the proof is for Cartesian closed categories. So the bad news is that it's an open problem. And I asked people that are experts in the field around, and was just given the answer, yes, it's interesting. So, but the bad news is not so bad as it might seem, because if you move from the category of metric spaces to the category of algebraic spaces, which is very popular in computer science, I am really surprised that Botkin and company did not use that one, but surprised, also disappointed. So then it works. So first of all, what does it mean? Well, algebraic space is one where the famous triangle inequality can be strengthened. Instead of plus, you get max. And so in this area, strongly finitary functors compose. The category of ultrametric spaces is then behaves in an analogous way. It works filtered colimits and certain weighted colimits that I don't have time to tell you about analogously, and therefore one gets bijection between strongly finitary monads on ultrametric spaces and ultrametric enriched quantitative algebras. And the proof in this case is, although the result is so analogous, the proof is completely different, because of course here one doesn't have anything like reflexive co-inserters, so this way how CPO is built from finite sets must be done much more carefully, and he did it carefully. If anyone has a positive answer to this, then we have a complete proof that it also works for metric spaces. Thank you for your attention.
Questions? Comments?
Do you know a characterization of strongly finitary for categories?
I do, because I've read the PhD thesis of John Burke. So John Burke devoted his PhD thesis to precisely the analog that I did not mention, and I should have. So thanks for the question. Where one works in the category of small categories. And I didn't tell you what it is because it's complicated. Well, it's not so terribly complicated, actually. You have your category delta, and these reflexive co-inserters could be seen as that you work with So the weight that you work with is the restriction to natural numbers 0, 1, 2. And what John did was working with delta 3 as the weight on which he bases the characterization of strongly finitary endofunctors of cat.
So, if there are no more questions, let's thank the speaker again.